forward with our presentation. John's been patiently waiting for us to get done here. John, you got 30 minutes. Give us your best shot. If I find something I want to know, or if something you want to know, you let us know when you've got the ability to answer questions, and I'll send them coming.
Okay, well, you can ask them anytime. Just interrupt me if you want to, but doesn't matter. So let me share my screen and we'll get over there and do this thing. Okay?
Wow.
You're a busy guy.
Busy one.
Is that a sideshow or a slideshow?
Whichever you like. All right, tonight we're going to talk about an antenna that a lot of people know about, a lot of people like, a lot of people have, maybe a lot of people have built. And we're going to talk about it in a little different way, though, than most presentations you see on it, or most articles you read about the magnetic loop, or particularly most websites that you go to. We're not going to talk so much about how to build it, or how good it is, or how it works so much. But I'm going to talk about how to optimize it, how to get the best out of it. Because many of you may have magnetic loops, or may have used them. And that's what I really would like to talk about, how to make them work their best. Because there's a lot of misinformation out there. And some of this may sound like a little bit of stepping on toes, because there's a lot of opinions on how magnetic loops ought to be built. And some of it is pure rubbish, and a lot of websites show you very bad information on how to build magnetic loops. But so I'm not going to address so much on how good magnetic loops are, or what you can do with them, or even how to build them, although I am writing a book on how to build them. But we're going to really show you how to optimize them. So I'm not going to give you the optimum magnetic loop, but on how to optimize a magnetic loop if you're going to build or buy one. Here are a bunch of magnetic loops. I took these off of the internet. These are just pictures I gathered in random. If you search for pictures of magnetic loops, you're going to come up with the same set of pictures as here. Some of these are good. Most of them are terrible. You might think, oh, they all look pretty good to me. There aren't many good ones in this group, including some of the commercials, which you see up here on the left. Surprisingly, those commercial loops up the upper left are not as optimum as you may think as they should be. In fact, there aren't too many optimized loops here in this drawing, even though this is the common offering. And some of them are absolutely unoptimized here. There are very few optimized web designs. In fact, if you go out there looking for one to buy, or for information on how to build one, you're going to find very many unoptimized web designs. And you're also going to find many misleading ads in the magazines and on the internet. And you're also going to find very little sound principles on how to make a magnetic loop that is optimized, that really does its maximum job for the situation that you're going to use it in. Because there is no one magnetic loop that fits all, believe me. You're going to possibly need several if you're going to use it in various situations. There is no one fits-all magnetic loop, no one optimal magnetic loop. When we talk about optimizing an antenna, though, if you ask the average ham, what about optimizing an antenna? They don't really only think about one thing. This red monster here in the middle, SWR. That's what most hams, that's about the only thing they think about. If you mention the term, is your antenna optimized? Is it optimized for the lowest SWR? They don't think about many other characteristics of an antenna that may be optimized. Well, that isn't the only thing an antenna may be optimized for, particularly a magnetic loop. And that's what I want to talk about. A magnetic loop has many more things about it that need to be optimized if you want it to give you optimum performance. And here are the 6 items that I've singled out as the 6 characteristics of a magnetic loop, all of which should be optimized if you want the thing to work really well. And in fact, if you don't want to be disappointed, as a lot of magnetic loop owners are when they buy or they build a loop. And we'll go through each of these: relative conductor diameter, construction material, loop shape, self-resonance, and matching and tuning. All of these are elements or are characteristics of a magnetic loop that need to be optimized. If you want it to give you the best performance in the particular situation you're going to use it in, because the magnetic loop varies quite a bit depending upon where you're going to use it. Okay, so this presentation is not going to be about how a magnetic loop works. I think it's been around in the ham community long enough that a lot of hams kind of basically know how it works. And I'm not going to give you a big list of the pros or the cons of the magnetic loop. It is a good little antenna, and it's especially good because of its small size. And it's a very popular antenna for people with limited space. And I'm not going to show you how to build one, although I'm going to give you some illustrations here which may lead you in how to build it. In fact, quite a number have been built from the guidelines you'll see in this presentation. Instead, I'm going to show you how to optimize it, the steps to maximum performance of a magnetic loop, whether it's in buying one or in building one, because these will be the benchmarks to use if you're going to go out and buy one, or if you're going to decide to go out and build one. Factor number 1, and believe me, this is the biggie. If you don't remember anything else about magnetic loops, except this one factor, and forget all the rest of them, this is the one you should remember. Because magnetic loops, their biggest drawback, if they're not optimized, is low efficiency. They have very low efficiency, particularly at their low frequency limit. Now, it may surprise some of you that magnetic loops have a low frequency limit. If you read the glossy ads in the magazine, you may have the opinion that magnetic loops will tune any frequency. Just put the right capacitor on them and you can tune them anywhere. Oh, no, you can't. That's just not true. You may be able to do it, and some of the websites may put a big capacitor on their design, and they may tune down to a low frequency, but they won't be efficient down there. Most of your power will just go to making the loop hot, not making radio waves. So the relative conductor diameter is, bar none, the most efficient characteristic of a magnetic loop in buying or building. And if you build or you buy one, you must buy a magnetic loop that has fat conductors, or you're not buying or building a good magnetic loop. Let me show you this in a little chart here that I put together. And by the way, this is based on some very hard physics equations, which you can find on the internet. I can give them to you offline if you want, but they're readily available. The equations for the efficiency of a magnetic loop. What's the efficiency? How much power gets out as opposed to how much power gets wasted in heat. And that's a big factor in magnetic loops, the efficiency of it. How much power gets wasted in just heating up the loop as opposed to making radio waves. There's no standards for this. I've arbitrarily set the efficiency here in this graph at 50%. That is, half the power gets out, half the power gets wasted as heat. And that's 1 S-point down at the receiving end. It depends on how much you can tolerate. You can certainly make contacts at lower efficiencies. But just arbitrarily for this discussion, I've set the efficiency at 50%, or 1 S-point down. Notice what happens here for a 4-foot square loop. You'll find out later why I made it 4 feet and why I made it square. But don't worry about that. It'll work for a round loop as well as a square loop. As many of you think a round loop is the best shape, or octagonal loop, but it'll work just as well for an octagonal or square. All loops, all magnetic loops have the same set of curves, based on the diameter of the conductor. Notice what happens if you make a 4-foot square loop, how the efficiency falls off. If you make a 4-foot square loop out of 3 different sizes of conductor. Suppose you make it out of number 10 wire. Now, number 10 is a pretty fat wire. It's about 1/10 of an inch in diameter. Or suppose you make it out of a piece of coax. Now, a lot of websites will tell you, oh, get yourself a nice piece of RG8 coax and make yourself the magnetic loop out of RG8 coax. Or get yourself a piece of 3/4 inch copper tubing and make it out of that. That'll make a great magnetic loop. Oh, no, it won't. Notice here how much the efficiency of a 4-foot square loop falls off as the conductor size goes down. If you want efficiency of an HF loop, a 4-foot HF loop, on HF, you want it to work 10 meters down to 40 meters, you need a 2-inch conductor, not a number 10 wire inside a hula hoop, not even a piece of RG8, not even a piece of 3/4 inch copper pipe. You need a 2-inch pipe to make a good loop that'll reach down to 40 meters in a 4-foot diameter loop. And if the loop is smaller, it's even worse than this. So don't let yourself be fooled to think that you can put a piece of fine wire inside a PVC frame or a hula hoop and get yourself a good magnetic loop. You can't. It's just basic physics. You'll get eaten alive by inefficiency if you do. Basic rule: fat conductors are absolute necessity in a magnetic loop. Don't ever think otherwise. Okay, let's do a takeaway. Something you can take away with you after this lecture. And if you don't take anything from this lecture, take this next picture that I'm going to show you away with you. Get out your mental camera, take a snapshot of this next loop I'm going to show you, embed it in your mental memory, put it in your mental toolkit for evaluating magnetic loops, whether it's one you're going to buy or one you're going to build, whether it's on that wonderful website that looks really great, or whether it's on that glossy ad in the magazine showing you that wonderful magnetic loop that they're trying to sell you. If it doesn't look like this magnetic loop, I don't mean exactly like it, but in general proportions, it's not a good loop. Here it is. This is an optimized magnetic loop for conductor diameter compared to loop size. Notice the size of the conductor compared to the size of the loop. It has a conductor that's at least 1/24 of the size of the loop. This to me is an absolute minimum if you're going to build a loop. If you make that conductor any smaller than a 24th the size of the loop, you're going to have very poor results on HF with this loop. Oh, it'll work, you'll make contacts. Lots of ham antennas are inefficient. The mobile whip on the back of your car is a very inefficient antenna.
Yeah.
And yet it makes contacts. But that doesn't mean if you want an efficient loop, this is what you need to remember. Embed that general image in your picture. By the way, this is a loop in my backyard. This one we're going to show you how this one's built here later on. The general ratio of a high-performance magnetic loop is something where the ratio of the loop size to the conductor size is better than 1/24. That's not a law, that's just a general principle. Now here's a good loop. Here's a good loop that follows this principle. This is the Italian-made Ciro Mazzioni mini magnetic loop antenna. It follows that ratio. It's a 6.5 foot diameter circular loop with 3-inch conductors. That one has big enough conductors. The conductors are fat enough in that one to make it down to 40 meters on HF. It has other limitations, as we'll find out later. But don't ever think that a magnetic loop can go down anywhere into any frequency. It can't. It has a bottom limit set by the efficiency of the size created by the conductor diameter. They must be fat. Factor number 2, and this is the big surprise to a lot of people. It's also a pleasant surprise because it'll save you dollars, or save you pounds, or save you yens, or save you euros, depending upon where you live. I give these lectures to clubs around the world, so I have to have this in multi-currencies, or Canadian dollars, whatever they be, whatever it happens to be, or pesos, or wherever you're making your loop. But this is a nice factor. The material you make the loop out of, and most hams have it wrong. Most hams are making their loops out of the wrong material. Not that they don't work, they may work fine, but they're wasting money by making them out of the wrong materials, in my book. Most of you know what skin effect is. You've heard about it as long as you've been in ham radio. Skin effect is where the current in a conductor flows only on the outside. Alternating current, as we probably learned a long time ago, only flows on the surface of a conductor. I have a whole presentation on skin effect, which you might want to see sometime later. But if you take that solid piece of aluminum wire over there on the left, all of the current is flowing on the surface. I've simplified it in this drawing. It actually tapers off as you go into the center of the wire. But in essence, all of the effective current is on the surface of that wire, particularly at radio frequencies. At lower frequencies, the skin is thicker, but at radio frequencies, at HF for example, that's pretty much where the current is in a piece of solid wire, on the surface, piece of solid aluminum wire. There's no current in the middle. What does that mean? We don't need the center. We don't need the center of that wire if we're building a magnetic loop or we're building an antenna. The center of the wire is just there to hold it up or to be there. We don't need it. It's not necessary for the antenna's function. The antenna functions entirely on the surface of that conductor. Notice how thin that skin is. It's amazingly thin. I've got a little graph that I put together of the skin depth on the various ham bands from 80 meters down to, or up to, depending on how you look at it, depth to 70 centimeters at the bottom, the 440 band. The lower the frequency, the thicker the skin. On 80 meters, you can see in aluminum, or aluminium, if you want to use the British pronunciation, it's only 1.7 mils thick. That's mils or thousandth of an inch. The skin depth, we need about 3 of them, but to give you full conduction. But notice how thin that is. 1.7 thousandth of an inch on 80 meters. At 440 down at the bottom, 70 centimeters, it's only 2/10,000ths of an inch thick. And in copper, it's half of that. It's extremely thin. So what does that mean in terms of a magnetic loop antenna? It means that foil, aluminum or copper foil, glued on top of PVC pipe, is just as good a building material to build magnetic loops out of as copper pipe is. Why waste your money on heavy, expensive, hard to work with copper pipe to build a magnetic loop with? It's ridiculous. No need to waste your money. Build it out of common, cheap PVC pipe and cover it with self-adhesive aluminum foil tape, and you can make just as good a magnetic loop with it as that one I showed you there a couple of minutes ago. So here's the best material to build a magnetic loop with. PVC pipe, stuff you buy at the hardware store. And you just miter cut the corners if you wish, or you can use elbows and put aluminum foil on the inside of them if you wish, or glue the corners together like this. And you can easily make magnetic loops this way and they work just as well as if that thing was made out of a solid bar of copper, just as well. It's amazing. Once I discovered this, I realized everybody that thinks magnetic loops ought to be made out of copper or aluminum tubing or bars or rods are wasting their money. Here's the optimal magnetic loop building material. Aluminum foil tape, self-adhesive tape. You can get it on the internet, you can get it down at your local hardware store for taping up air conditioning ducts, and it's inexpensive, and you can get it in rolls 2 inches wide, you can get it down to 1/4 inch wide, you can get it up to 4 inches wide, readily available on Amazon or down at your local hardware store. Easy to get stuff. Now I know some of you are going to say, but isn't copper better? No, copper is not better. Copper is more conductive. Yes, I agree copper is more conductive, but it has half as thick a skin. So the aluminum with 40% less conductivity, but with twice as thick a skin, is just as good. Use aluminum foil tape to make your magnetic loops out of, and put it over PVC pipe or PEX pipe or even cardboard or wood. Why not build a wooden magnetic loop? I've built them, and they work just fine. Get yourself some 2x2 and angle cut it on your table saw and nail it together, or use some lag bolts and put it together and put aluminum foil tape on the outside. Makes a great magnetic loop at a fraction the cost of trying to build it out of copper pipe. In fact, here's a price comparison. If you want to build a 4-foot square loop out of copper pipe, 1.5 inch copper pipe, which is 1.9 inches in diameter, which is the diameter you need for a good 4-foot loop, or 1.5 inch PVC pipe, which again is 1.9 in diameter on the outside, the cost comparison is incomparable. You're going to need 2 10-foot sections of it to build a 4-foot loop at $128 each in copper, or $16 or $17 in PVC. Who wants to build it out of copper when you can do it out of aluminum foil and PVC? No comparison. All right, loop shape. Now here's one that's going to step on a lot of toes, but there's many advantages here that'll be gained by paying attention to this one. There is an optimal loop shape too, and it isn't what a lot of you are thinking. The magnetic loop came out in 1968. It's a relative newcomer to ham radio. Came out in this article in 1968, marked QST. By the way, you get a copy of this if you want. I got a copy of it from QST on the archives there. They have a copy of it. That an article that Lou McCoy, now deceased, now Silent Key, saw an article by Ken Patterson from the Army Limited War Laboratory, who developed the Army loop for use in Vietnam, for HF activities in Vietnam. And there's Ken Patterson adjusting his Army loop made out of 5-foot sections of aluminum tubing, flattened and bolted together at the corners. And from that day onward, hams have thought that the best shape for magnetic loops is an octagon or a circle. And that's stuck in the mind of hams. But you know, circle or octagon is not the optimum shape for a magnetic loop. It just isn't. And let me show you why. Back in the middle of the 19th century, Michael Faraday, the great radio experimenter, great pioneer of radio, studied magnetic loops. He was a fan of magnetic loops. And he realized that magnetic loops all work by only their area, their square area of the loop is the only thing that determines how they work. So here's the comparison I've shown you here. The dotted line is a circular loop, or a circle of a given area. The blue line is an octagon of the same area, and the square is a square of the same area. How much difference is there in those three in terms of just physicality? Very little. The square loop only sticks out a little bit at the corner. Why trouble yourself to try to make a circle or an octagon? The easiest loop to make is a square. Why if you're gonna build it, if you're gonna go to the trouble of building it out of copper pipe, you buy a bunch of 45-degree elbows, which cost a fortune, or trying to bend the thing into a circle, particularly if you're gonna build it out of big enough pipe. If you want, really, these 3 loops that I'm showing you here are all too small in diameter by the first criterion I show you. How are you gonna bend inch and a half copper pipe into a circle? But you can certainly make an 1.5 inch square loop, easily. Square is the optimal shape for a magnetic loop, not round. There's so little difference in the effective size. Make it square. Square PVC aluminum foil coated loop is the optimum magnetic loop, not copper pipe. And here's another reason why I say this. Here's your friendly neighbor looking over the backyard fence. What is he going to think if you have an octagonal loop, or you have a round loop, or you have a square loop? Which one is he going to notice? Which one is that nosy neighbor that comes wandering down the street from your homeowners association and looking over your back fence, seeing what sort of nasty things you're doing in your backyard there? Which shape are they going to notice when they look over the fence if they see an octagonal loop? What's that ugly thing in your backyard? Which one are they going to notice? They're not going to notice the square. They're probably going to think it's a rose trellis. But they're certainly not going to think an octagon is a rose trellis. In fact, the square loop, you can probably hang a few plastic roses on it and fool them completely. So the square loop is a much better shape to put in your backyard than an octagon or even a circle. So it has another advantage. This one might be the biggest advantage of them all. All right, factor number 4, self-resonance. How many of you who have built or are buying a magnetic loop even know that this is a factor? How many of you even know that a magnetic loop has a maximum frequency that it can operate on? Well, it does. It's determined by its self-resonant frequency. What is its self-resonant frequency? Okay, let's show you that. Here's the basic magnetic loop. In a square, it could be a circle or an octagon if you wish, but we're sticking with square here in this presentation. Here's a basic magnetic loop, just the raw loop, nothing but the loop. It's a half-wave length loop with a gap at the top. All pieces of wire, whether they're straight or whether they're wound into a loop like that, a coil, have distributed inductance and distributed capacitance. Even a straight piece of wire has capacitance and inductance natural to it. It's a natural property of all conductors. And therefore, that natural inductance and that natural capacitance in all pieces of wire, all conductors for that matter, have a natural self-resonant frequency that made up of that standard formula for L and C to make up a resonant circuit. Every manufacturer of coils knows that their coil has a self-resonant frequency. All coils have a self-resonant frequency. And what is a magnetic loop? It's just a coil, a one-turn coil. It has a natural self-resonant frequency. But here's the principle. A magnetic loop without a capacitor can only resonate, can only be tuned to its self-resonant frequency. And here's the self-resonant frequency of various diameters of magnetic loops. You can see that the self-resonant frequency by the size of the loop, shown here by this graph. So you'll see that a 4-foot loop here, if you look there to the bottom left, has a self-resonant frequency of about just above 30 megahertz. So you cannot get a loop that's bigger than 4 feet to resonate above below 30 megahertz. it just won't work. So the self-resonant frequency of a 4-foot loop is 31 megahertz. A magnetic loop can't be tuned any higher, a 4-foot loop can't be tuned any higher than that. You can't add capacitor to a 4-foot loop and get it to tune higher than 31 megahertz. So if you want to make a magnetic loop that'll tune above 31 megahertz, you got to make it smaller. All magnetic loops have an upper frequency and a lower frequency. Don't let the ads fool you. You can't tune them to any frequency. Here's the various self-resonant frequencies that you can tune a loop to. A 16-foot loop, you can't tune it above 7.8 megs. An 8-foot loop, you can't tune it above 15 megahertz or 20 meters. You can't tune a 4-foot loop above 10 meters. If you want to do a 6-meter loop, you got to make it 2 feet in diameter. So depending upon where you want to operate that loop, you've got to make it the right size. So don't let anybody tell you that one loop will work anywhere. It won't. If you want to really cross the HF band, you may need more than one loop.
I got a question for you, John.
Sure.
Isn't the standard principle of that loop a quarter wavelength of the operating frequency for the diameter of the loop? Or the tuning stuff, isn't it supposed to be like a quarter wavelength of the operating frequency, and that's where that's how you know where you want to start, and where it's going to be?
It's a half wavelength loop around, that's what it is.
I thought the dimension was quarter wavelength of the operating frequency.
Not that I know of.
Okay, well, that's what I read someplace, so that's why I was asking.
No, it's a half wavelength loop with a gap at the top.
Right.
And that's, anyway. So here's this Ciro Mazzioni loop. That loop can't work above 25 megahertz. It's too big. So realize the resonant frequency of the operating frequency of a magnetic loop is limited at the upper end by its self-resonant frequency, and it's limited at the lower end by its efficiency. So don't be fooled by the glossy ads. No one loop can work all the HF bands. Okay, let me give you an optimized example. Here's the one I showed you before. I've moved on a little in this design, but this is still remember, this loop is not a how to build it, this presentation is not a how to build it presentation. Although many people who've seen this presentation have built this loop, and many of them have been on the air. So if you're a enterprising builder, you can pretty much build this loop pretty much from what you see here. It's pretty self-evident what to do. And you can see it's a 4-foot loop. 45 inches are the length of the actual pieces of tubing. The outside dimension is 48 inches. Outside to outside, the pieces of pipe are 45 inches, covered with aluminum foil, and two overlap pieces of 4-inch wide 4 mil aluminum foil that I got off of Amazon. And the corners are standard 1.5 elbows and 1 T. You'll see the function of the T, you'll see here in a minute. And they're cut in half vertically on a bandsaw, and they're screwed to the loop with sheet metal screws. The inside of those elbows is covered also with aluminum foil to give conductivity around the corners. The aluminum foil tape inside overlaps with the foil on the pipes. The structure down at the bottom is the coupling loop, which we'll show you a bit later. This is a good efficient loop from 10 down to 20 meters. And it's okay. It's a little drop off in efficiency at 20, but it's a good loop. And the tuning capacitor we'll talk about later. This is a simple, easy to build manual tuning capacitor. You can use this. I'll show you here a vacuum variable or a rotary if you want. And some people who built this loop have used rotaries with this design. I'm going to show you here a simple manual one. here's the actual design of it in drawing. And by the way, you can download this whole presentation that you're seeing here tonight from my website, W6NBC.com, W6NBC.com/magloop. And you can download this whole presentation, all narrated, you'll get all these slides, and you can view this presentation later if you want to, which will have this drawing in it. And you can see it's a 4-foot loop. It has a foil gap of 1 inch at the top and a little mounting plate at the bottom, which mounts the little tuning or coupling loop, which is adjustable. And it has a little a piece of 2-inch pipe that holds it up with a half cut off T at the top to act as a saddle support. And very easy loop to build. Now, putting the foil on the pipe is a little bit of a job, but I finally deciphered a way that makes it quite easy. I'll just show you this quickly. Putting self-adhesive anything on anything is pretty tricky. If you've ever tried to put shelf paper down on kitchen cabinets, you know how difficult it is to get self-adhesive stuff down on a surface nice and smooth without wrinkles. Here's how you do it. You take a piece of tape and you cut it long, you fold over the ends, you fold back a little piece of the end to expose a little tab of the tape, and you stick it down on a piece of carpet like this. Then you snip off the ends, and then you can roll it, and then you pull off the remainder of the backing until the glue's up, and you push the pipe down onto the glue. Now you can roll the pipe back and forth and get it on nice and smoothly. Here's the foil inside the cut in half elbows. They cut in half pretty easily with a bandsaw or a hacksaw, and then you cut a little 90-degree elbow piece of the
Somebody froze.
little doing. You might have to do it once or twice until you get it right, but it didn't take me too long to learn to do this correctly. And those nice smooth round surfaces there with the hole through them is where the tubes with aluminum foil on it couple to the elbows at the corner. And that overlap is enough overlap to make a good connection. They're held together with sheet metal screws, as you can see. Okay, finally the matching. The matching network, there are various ways of matching the loop, as any of you who built a loop and so forth know. This is the way I generally prefer. The common way to match a loop is to use a separate loop. This is good method, works well. It's an efficient or an optimum method. I just find it a little flimsy, but it's an RF transformer. Works very well. Many of you who've built loops or know about loops know how this method works. You simply put up a little secondary loop that's about a fifth the size of the main loop, and you then either pull up or push down on this loop until you get a good match. It's very easy to get a good match. Here's a undersized loop that somebody built out of copper pipe with a little matching loop made of a piece of ordinary solid house wire. And that's a good matching method. It's a simple RF transformer. Or you can use this method, which is a modified gamma match, and that works very well too. I don't like this method, but it's a pretty good method of doing it. You hook the shield of the coax to the opposite the tuning capacitor, to the low impedance side of the loop. The high impedance side is where the tuning capacitor is, and then you tap up the coil. This is just like tapping a coil inside a radio, inside of a transformer in a radio. This is an auto transformer. This is another common method of matching the loop. Like I said, I'm not going to explain the theory of magnetic loops. You can find these matching methods on the internet quite commonly. And this is the method I generally prefer. And this is essentially how this physical method that I prefer tends to work. It's 3 pieces of 1/2-inch aluminum tubing that the end has been flattened and they've been drilled with a 1/4-inch drill to allow me to use 1/4-inch stainless bolts and nuts to form a movable matching loop. And there's a U-bolt that goes around the tubing, and to allow that whole assembly to be moved up and down the pipe, or it can be even brought down onto the bottom pipe if you want. But by moving that coupling loop around, you can easily obtain a match. And as you'll notice, the coupling loop, the end of it hooks over to the center conductor of a SO239, which is mounted on a little plastic plate. I just flattened out a piece of PVC pipe by heating it up and then squashing it flat and sawing it flat, or any kind of plastic. Piece of plexiglass works fine. And then putting some foil on that piece of plastic, and then attaching it to the loop with the through bolt that mounts the loop, and another sheet metal screw to stabilize it. It's an easy structure to make a coupling loop, and believe me, that coupling loop can easily position with a little bit of doing to get a perfect match to this loop. Works very, very well. This is an RF auto transformer, or a tap match, as you might be familiar if you go back in the days of radio when you had a little coil inside of a transformer can where you just tapped up the coil. Okay, tuning. Still in development. This whole antenna is. You can, if you wish, use this same design with a vacuum variable, although since most of these were made in Russia, the reasonably cost ones, they're hard to get these days with the thing happening there in Russia right now these days. Or you can use a rotary tuning capacitor, which are quite common, although rotary tuning capacitors tend to have a lot of loss in them due to the wipers inside of them. Several people who have built these loops, just from this information you see in this presentation, have used rotary capacitors. They're handy. And of course, these two methods allow you to remotely tune these things if you want to. My method is a more simple method. Here's one of my builders who built one of my loops, and he used a rotary capacitor in a box. Here is my optimal low-cost optimization. This is an internal tuning capacitor. I don't favor this method anymore, but it works very well. It uses an internal tuning capacitor inside the loop. You put a little pipe inside, which goes through that side elbow, another piece of smaller PVC pipe, which has aluminum foil around the end, and you slide it in and out. And if you put it in the right, overlapping the gap, you get maximum capacity. And if you pull it to the side, the one capacitor gets small and the other one gets bigger, and the capacity gets less. And I use that for fine tuning. And then there's a bigger capacitor that goes on the outside, which is a piece of PVC pipe, the next size up, cut in half, and some aluminum foil put on it. And I use it as a band tuning capacitor. So you set a capacitor on top of the outside to set the band, and then you slide the one inside back and forth to do the fine tuning. And with this manual tuning, you can easily tune this loop for very little money. There's the inside slider. As you can see, it slides in and out of the end of that T-fitting, which you saw earlier, and it was about 12 inches long. And the outside capacitor for 20 meters was a 14-inch piece that's set on top. You can make these outside capacitors for other bands, and you can do the fine-tuning with the one on the inside. This method works very well. Believe me, this whole presentation is a loop still in development. I don't mean these as cookbook methods, but I think any of you who are enterprising builders will be able to turn this into very working loops. I've had at least a dozen of these loops built, and they're very effective. I'm now working on a 10-meter one for On the Air magazine for the newbies for use on FT8. I think it'll be a great little loop for FT8, and that's where a lot of people are using it. Here's the inside capacitor tuning. That smaller pipe pulls in and out of the loop from the end. Now, if you're a real enterprising builder and you want to automate it, Never mind, I took that part out. Now, here's some takeaway specific.
Hey, John,
Yeah,
I'm getting cramped up on time here, we're already about 45 minutes into it, we were supposed to be
okay.
done at 30.
I'm almost done, I'm sorry to go a little
Rock and
longer.
roll, no problem.
Okay, I'll end real quickly here. Multi-turn loops are very good, so if you want to think about doing multi-turn loops, you can. Multi-turn loops improve with size squared. So if you build a 2-turn loop, it's 4 times as efficient. Don't do this. Don't use flat conductors. Don't do this. Don't stagger the loop. That's a bad idea. You're going to lower the efficiency. And don't try to do this. Don't try to wind a helix around the pipe. It doesn't work. And don't use a horizontal loop. They have bad radiation pattern. Okay, here are the 6 things. Optimize your loops. You'll be happy if you do. You build one, send me pictures and photos. Here's my little doggy. No, she doesn't have a German call sign, and she's not D0GGY. There you go, there's my call sign. You can contact me any day, jportune@aol.com, and through my website, W6NBC.
Wow, thank you very much, John. I can't believe that you went 40 minutes and you didn't stop once, man. That was unbelievable. What a presentation. I mean, really, that was phenomenal. That was probably one of our best presentations. You got all that information out there. That was just unbelievable. I thank you very much. We all thank you. Anybody have any questions for John?
Get 3 more and make it
Coley's got a question.
It's not a question, but it's a note that I've seen before. I used to belong to.
You may have to relay the question, I'm not
Yeah.
understanding.
Can you hear?
No, he can't hear you. Just tell me and I'll tell him.
Okay, I've seen people make one of these things with a water bottle up on the top. And then they had a syringe, and you could change the tuning by pushing the water bottle.
Yeah, he said he saw somebody put one together with a water bottle on top, and he used the syringe to take the water in and out as the tuning capacitor.
Oh, wow, now that's an interesting idea.
Yeah.
Until it freezes.
And the other question I have is.
Still the
winter.
Put some,
Don't think that far.
specific salt in there to make
Yeah,
it more
he's in
conductive.
California,
Yeah.
so.
Oh, that's true.
A fluid tuning capacitor, I never thought of that one, that's a great idea.
QSD has a homepage ad, and what they seem to be pushing is their tuning box
Oh,
on that thing, which is probably more than transformer, but in any case, is it worth even looking at that thing?
probably not, according to what he just told
Yeah.
us. It's just somebody marketing. Sure.
Ask him if the foil gap is critical on the top as far as width.
Yeah, is the 1-inch gap at the top of the loop critical or
No,
anything?
not at all.
Not at all.
I've had gaps from 1/2 inch to 2 inches,
All right.
it doesn't make much difference at all.
Okay, and then the next question is gonna be, can we put a gigawatt into it, or are we limited?
Well, a lot of people are afraid of using foil, thinking they're gonna burn it up. You'll be surprised. I'll just give you a little quick rule of thumb. Do you think a piece of 3/8 inch aluminum tubing will handle power?
Yeah, I mean, I see it on a beam antenna all the time.
A piece of 1 inch wide aluminum tape, 1.5 mil thick, will handle the same amount of power.
There you go. All right,
Yeah, I got a question.
okay, one more.
Hey, you know, if you were gonna buy a commercial one, which one would you buy?
According to him, I wouldn't buy any of them.
Well, I know, but that's what
But
I'm
if
asking.
we were gonna buy a commercial one, which one would you recommend? If we only had the only option we had was to buy one that's already made.
I don't know of a commercial loop out there I'd buy.
Right,
That's-
I agree.
That Cyril Mazzioni loop is fine within its limited range, but it's very expensive, and it has pretty narrow frequency limits.
In other words, the ones that you could buy at the store you're just kidding yourself. It's a
Yeah,
gift.
pretty much,
It's a gift.
pretty much. And boy, the ads are glossy, they'd convince you this is a wonderful loop, but it just isn't.
Okay. Yeah, John.
Ask John when his book is coming out.
Yeah, when's your book coming out, John?
I don't know. You know, too many things to do and too little time.
No, I got you.
It will be. I've got about eight of 10 chapters written, so it's not far off.
Okay, is there a limit on the height? In other words, does it have to be so far above ground before it becomes efficient? Can it be on the ground and be efficient?
Magnetic loops are quite good near the ground. That's one of their qualities. So they work. But they're much like other antennas. Height helps them, of course, but they're not as sensitive to the ground as more linear antennas are.
Okay, the final last question is, are they directional if you rotate them?
Oh yeah, absolutely, definitely directional. They have a pretty much a figure eight pattern like most dipoles.
One more question, go ahead.
A lot of people I see that have restrictions on antennas, they'll run them inside their house. How efficient are they?
They're not.
They're not efficient inside?
Well, no, if you're standing next to the thing and it's not efficient to begin with, it ain't gonna be any more efficient if it's inside the house. And you've got a hamburger hanging off of it or whatever. Anything else?
Can we flash the last slide again to get a picture of it?
Can we do what now?
Flash the last slide to get a picture?
Well, the whole presentation is gonna be available on our website and his. So you can
Yeah.
download the whole thing.
W6NBC.com/Magaloop. You can download the presentation.
How about the plans? Are they available on that presentation?
Well, that diagram is in the presentation.
There you go. Yeah.
That diagram is pretty much, if you're any sort of a builder, that
Okay.
diagram has enough.
Was the government using it in Vietnam for NVIS?
Was the government using that Vietnam thing for NDA? I think they were just using it for HF communications in the field because it was small.
Yeah, the government has a 3-turn loop that they use all the time, made by Harris Communications. They're still using HF loops, but they use a 3-turn loop because it has greater efficiency. And we could build 3-turn loops too. They don't use HF as much anymore as they used to.
Okay. All right, anybody else? Well, John, I'm gonna say goodnight and thank you again very much, and hopefully we'll get another opportunity to.
Anytime, have me back anytime.
Oh, man, thank you very much, John.
Oh,